A quiet assumption sits beneath almost everything we experience. It dictates that objects exist independently, and that physical distance creates an absolute barrier between them. A cup sits on a table, separated from a chair by empty space. But at a certain scale of observation, that assumption fractures. For centuries, physics reinforced this perception of space. Isaac Newton described a universe that behaved like a vast, precise machine, governed by a set of predictable rules. In this classical model, every object possessed a definite state. It had a precise position, a specific velocity, and a future trajectory that could be calculated if you gathered enough information about its present condition. This framework provided a safety net for human perception. It promised a stable reality where the boundaries of physical objects were absolute and understandable. The first cracks in that stability appeared when physicists began examining the microscopic world. Tiny particles like electrons and photons refuse to behave like solid, independent objects. Before it is measured, a particle doesn't hold a single, fixed property. As this diagram illustrates, it exists in a condition known as superposition, a state where it embodies a range of unresolved potentials rather than settling into one outcome. In classical uncertainty, a coin hidden under your hand is already heads or tails. You simply lack the knowledge. In quantum mechanics, the coin exists as both outcomes simultaneously until the moment a measurement is made and it is forced to declare itself. This transition from objects to potentials requires a different way of looking at the physical world. Subscribe now to follow this investigation as we map the evidence that led physicists to question the very nature of physical separation. While superposition shows that individual particles are unresolved, it prepares us for a more significant interaction, one that suggests 2 points in space can behave as if they are not separate at all. The limits of space are tested when 2 quantum particles are created together or come into close contact under specific conditions. This visualization shows the interaction. The particles merge, losing their separate states. Their outcomes become dictated by a single mathematical object known as a joint wave function. Even as physical distance grows, they remain expressions of the same underlying system. This specific interconnected state is what physicists call quantum entanglement. It implies that space does not always act as a separator. In this system, 2 distinct locations in the universe can hold the exact same entity simultaneously. To maintain a sense of order, people often use the analogy of a pair of gloves. If you tack a left glove in a box and send it to Tokyo, keeping the other in New York, opening your box to find a right glove instantly guarantees the distant box holds the left. The outcome is predetermined. But entangled particles possess no hidden labels or pre-decided states while they are traveling. Both particles remain unresolved. Even when separated by interstellar distances, they exist in a genuine state of superposition. Then, a measurement occurs. Observing one particle forces the distant particle to instantly snap into the corresponding opposite state, bypassing the physical space between them. There is zero time delay. No physical signal travels from point A to point B, not even at the speed of light. The correlation happens outside the bounds of spatial geometry. The particles react as a single unit, because mathematically, they never truly separated. The rule that objects have definite properties and that any influence between them requires time to cross a physical distance is known as local realism. Entanglement contradicts both pillars of this idea simultaneously. It shows that the outcome of one measurement is linked to another across any distance, and that particles do not possess definite properties until they are observed. Albert Einstein found this behavior so problematic that he famously dismissed it as spooky action at a distance. His objection was rooted in the structure of reality. If entanglement was accurate, then reality was not built from independent, localized parts. It meant the spatial division we perceive in everyday life is an emergent feature rather than a fundamental law. The phenomenon presents a strange paradox. Despite the instantaneous connection across space, the outcome of measuring any entangled particle is entirely random. Because we cannot control the result, we cannot use the correlation to send intentional messages. The universe allows these outcomes to mirror each other across galaxies, ignoring the structure of physical space, while strictly preserving the rules of causality. To resolve this, Einstein proposed that unseen, pre-programmed instructions, what he called hidden variables, must be secretly embedded inside the quantum particles from the very beginning. The physics community faced a defining choice. Was Einstein right that a hidden layer of data could restore the classical model of the world? Or does physical distance simply not exist at the quantum level? In 1935, Albert Einstein was deeply unsettled. He and two colleagues, Boris Podolsky and Nathan Rosen, published the EPR paper, challenging the mathematical consistency of the growing theory of quantum entanglement. Einstein defended the concept of local realism. He argued that physical properties must exist independently of whether anyone is looking at them. If particles seemed to coordinate across vast distances, they had to be following hidden variables, unseen pre-programmed instructions that maintained a predictable, machine-like universe. Niels Bohr immediately rejected this premise. He argued that the act of measurement defines the state of the particle. In Bohr's view, a particle has no definite properties until the moment it is observed, making any question about its prior state meaningless. For decades, this debate remained a total stalemate. Both physicists used the same data to reach opposite conclusions. Because no laboratory at the time could physically test these correlations, there was no way to prove whose interpretation was correct. This wasn't a clash over math. It was a battle for the definition of existence. It questioned whether the universe is made of objective, independent parts, or if reality itself is created through interaction. The deadlock broke in 1964 when physicist John Bell translated this philosophical conflict into a mathematical limit. This line graph illustrates Bell's inequality. That solid upper boundary represents the maximum statistical correlation any theory involving hidden instructions can produce. If experiments showed entangled particles producing stronger correlations than this limit allows, Einstein's hidden variables could not exist. By the 1970s, technology made the test possible. Physicists fired entangled particles through precise detectors, and the results were unanimous. Bell's inequality was violated in every trial. This eliminated the possibility of hidden instructions. The particles are not following a pre-written script. Their outcomes are genuinely unresolved until the moment of measurement. Because no signal travels between them and no hidden variables guide them, distance becomes irrelevant to the system. The universe is non-local. Entangled particles behave as a single entity, regardless of the physical space between them. This non-local behavior upends how we study the world. Physicist Leonard Susskind noted a strange inversion in entangled systems. The whole system possesses information that the individual parts do not. This breaks the logic of classical reductionism. For centuries, science assumed understanding a complex system required breaking it down into its smallest components. Entanglement suggests that some truths only exist in the relationships between parts, not the parts themselves. Look at this network of nodes. As a whole, the system has a clear, predictable state. But as the view isolates just one individual component, the information vanishes into a hazy cloud of probability. In an entangled system, you can know everything about the collective state, yet find the individual particles to be completely undefined.
If the universe is built on these hazy potentials and non-local links, we face a massive contradiction in our daily lives. Why does a coffee cup on a table appear solid, separate, and fixed in one place? Our experience of a stable world is at odds with the proven laws of physics. There must be a specific mechanism that masks this quantum chaos and creates the solid reality we see. That mechanism is decoherence. It is the process by which sharp quantum connections are diluted by the environment. A quantum system in superposition is incredibly fragile. The moment it interacts with the outside world, like colliding with air molecules or thermal radiation, that isolation ends. As the diagram shows, the system instantly entangles with thousands of surrounding particles. The precise quantum information leaks outward, fracturing into a complex web of noise that is impossible for us to track. The quantum nature of the particles hasn't vanished. The connections are still there, but they are so widely distributed across the environment that they can no longer be observed as a coherent whole. This chaotic entanglement averages out into the emergent stability we call the classical world. The solid objects we interact with are not the foundation of reality. They are a simplified byproduct of entanglement spreading beyond our reach. Why does a non-local, interconnected reality feel so wrong to us? Why is the mind so resistant to these proven facts? Our brains evolved to navigate an environment where objects are large and interactions are local. Evolution prioritized the speed and efficiency needed for survival over a perfectly accurate model of the subatomic world. Concepts like distance and separation are cognitive shortcuts. They provide the reliable results we need to function in daily life, even though they failed to describe the universe at its most fundamental scale. This biological limit is why physicists define the quantum world by what it is not. They describe it as not classical and not local because our language and intuition have no direct equivalent for how it actually behaves. True understanding now requires us to let go of the need for a clear mental picture. We have to accept a structure of reality that actively resists human visualization. At its depth, reality is not a collection of independent things. It is a continuous, unfolding process of relationships. The classical world remains a reliable framework for large-scale objects. Its laws of cause and effect provide the stability necessary for our survival, even if they don't capture the underlying quantum behavior. The model of reality we inherited was never built to describe the universe at this depth. The predictable, localized world we navigate has always been the surface of an ocean defined by shifting correlations. Exploring these concepts takes a high level of curiosity and focus. Thank you for committing your time to watch this video all the way to the end. If you found this dive into non-locality useful, please like and subscribe for more research-based content. To see how these principles lead to even stranger phenomena, click the playlist on your screen now. See you in the next one.